Hello everyone, I'm Lieutenant Colonel Judah, and I just want to briefly describe the differences between the perfect gas law you may have learned in chemistry and the one we're going to use here in Aero. But before we start, I want to look at this awesome photograph. This is the F-22 Raptor in a turn, and it's pulling enough G's that it's creating such a low pressure system, probably in a moist air environment as well, that the vapor created as the moisture coming out of suspension due to the low pressure, low temperatures over the wing. We're going to learn about all of this as we proceed in Aero 210 and Aero 315. But let's get into this short lesson on the differences here. Now, by this time, you have learned that there are four fundamental point properties that help describe airflow in Aero. And those are going to be pressure, density, velocity, and temperature. And there happens to be an ideal gas law, a simplified one, that helps to relate three of those properties that we're going to use very prominently in Aero. That is, pressure is equal to density times a gas constant for air times temperature. Now, how did we get there? You've seen it primarily as pressure times volume equals the number of moles times a universal gas constant, we'll say R bar, times temperature. Don't forget, temperature has to be an absolute, Kelvin or Rankine. So the way I like to do this, and I'm sure the chemists have a more elegant way of doing this, but in my engineering aeronautical mind, this makes sense to me, and I think it should for you too. I'm going to look at the universal gas constant, R, to begin with. R bar is 8.314, and that's going to be units of joules, moles, Kelvin. Okay? Well, if I'm going to be specific and have a gas constant just for air, why don't I use the molecular mass conversion? 1 mole per 0.2897 kilograms of air. Okay. Now the moles will cancel out. That's handy. And I'm going straight to kilograms. It's normally represented in grams, but for the sake of time here, I'm going to go skip straight to the kilograms. Now this is going to be a new R. We define a new R for air now, which is equal to 287 joules per kilogram Kelvin. And incidentally, this can be found on page, you should know this, 569 in your text. And there's two of them, one for English and one for the metric unit system. So this is the one for the metric unit system. So to be more precise, the equation should now be rewritten as pressure times velocity is equal to mass times the gas constant for air, since we're using kilograms, times the temperature. And I'm going to do some quick algebra here and move the volume over under the mass. Hopefully you'll understand that math step. I don't have to demonstrate it too much. Mass divided by volume times the gas constant for air times the absolute temperature. Well, what is mass over volume? Happens to be density, stuff in a box. Mass per area cubed, or per length cubed. So now we rewrite the final form of our equation. It's going to be pressure is equal to density times the gas constant for air in this case, times the absolute temperature. And that's the perfect gas law that we're going to use here in class in Aero 210 and Aero 315. Don't forget that we make some assumptions with a perfect gas. In this particular case, we're assuming it's dry, there's no molecular interactions, they're perfectly elastic, and that we assume zero volume using the perfect gas law, and that these things operate in a moderate temperature and pressure environment. And by and large, this works out very well for our calculations in engineering. I hope you've learned a little bit from this short video. I'll see you in class.